We've all seen this in one form or another, a solution of copper-2 ions, either from the source of copper nitrate or copper sulfate. Any soluble copper-2 salt dissolved in water will produce a blue color, you can tell, and then you put either a galvanized nail, which means it has a zinc coating, or a strip of zinc into it, and you spontaneously see the redox reaction occur. The copper ions are reduced to copper solid, and the zinc is oxidized to zinc 2+, and that occurs until the limiting reagent is used up. And so that's a simple redox reaction, and we know from the activity series from the first semester that zinc is higher in the activity series. That means it's going to oxidize sooner than it's going to oxidize. It's going to be oxidized by anything below it, and so copper is below it. And anyway, we can look at a different kind of chart. It's related to the activity series, but these are electron potentials, and for now it's very small and there's a lot of reactions here, but these are all listed as reductions, okay, and they're half reactions, and there's a voltage next to it. We'll look at that later. For now, we'll just look at these redox reactions. And so if you find the copper, and so if you're looking for copper metal, you're going to need to look on the right side, because these are all listed in as reductions. And so we also want to look for the zinc. So what that means here is that copper is going to oxidize anything that's below it. Okay, so copper is going to cause this reaction here that's listed as a reduction to proceed in the reverse reaction spontaneously, right? So does that mean that we cannot go back? Well, that's not true. We can apply a current or a voltage to it, and we can reverse this, but we have to do it a little bit differently here. We have to set up what is called an electrochemical cell, where we have two different cells or beakers where the reduction and the oxidation are separated from each other. All right, so here we have the oxidation in the left beaker here, all right, and the reduction takes place in the right beaker. And so they're basically connected by a wire, so electrons can flow, and we can prove that by putting a light bulb in the middle. But you also have to have an electrolyte present, and so here we're connecting the two solutions, the two half cells, with a so-called salt bridge. And it doesn't matter what ions are in there, just some sort of electrolyte. Potassium nitrate is cheap, it's readily available, so that's what we use in this particular case. And so what happens is at the end, the anode is going to be the electrode at which the oxidations takes place, and the cathode is the positively charged electrode where the reduction takes place. So we've got electrons being produced at the anode, and they are flowing this way, and you can do work with this electrical energy. And so the light bulb is the work that we see as these electrons are flowing, and so this is called an electrochemical cell. And there's actually a voltage that you can measure or predict, and so just for some vocabulary, if you have an electrochemical cell, you have to have a salt bridge between and a wire between the the oxidation and the reduction, or you're not going to be able to observe a voltage. If that particular electrochemical cell reacts spontaneously, we call that a voltaic cell or a galvanic cell. But you can also, by applying a voltage or a current or some sort of energy, we call that the electrolytic cell. We can make this reaction go backwards, right? And this is how rechargeable batteries work, right? We can make a process go backwards, and then it can go in the spontaneous direction to produce a current again, so that we can power our little radio or whatever your battery powers. Anyway, that's just some vocabulary. Here's some more vocabulary that you can look at on your own, but we measure the energy of electron flow in volts. And it's also important to note that we'll use this later on here, that 1 volt is equivalent to a joule per coulomb, and a coulomb is just is related to the charge of an electron, and if you have 1 mole of electrons, the charge would be 9,648 Faraday. But we'll come back to that later, so you can look at that yourself. It's just vocabulary. So now we're going to go back to the electrochemical cell, and so this is a different, no, this is that reaction, the copper oxidizing on the left, and sorry, it's the zinc that's oxidizing, producing 2 electrons. Electrons are produced here. As you can see here, zinc ions and electrons are produced, and they flow through this wire, and they are then taken up by copper ions, and so we have a copper electrode. These electrodes don't have to be copper or zinc. We have to have, obviously on the anode side, we have to have a source of zinc, but on the product side, we don't. You know, we can have also a zinc electrode there, and the copper would precipitate or deposit on top of that wire. But in this case, the cathode here is part of the reaction here, right? So so we have this notation. Instead of drawing out an elaborate picture every time, we just write it like this. You have the 2 lines in between the oxidation and the reduction. The oxidation is on the left, the reduction is on the right. The double lines means there's some sort of electrolyte, that's your salt bridge, and then we put a line between the electrode and all of the ions. In this case, there's just zinc ions in the oxidation, and there are copper ions in the reduction, and so the electrode is copper here. So basically, it's the electrode, the electrolyte, at least those electrolytes that are part of the reaction, then the salt bridge and the electrolyte of the reduction, and then the electrons again. And so sometimes when these reactions are more complex, like here we have an oxidation that's simple, we just have an iron electrode, and the electrolyte is just iron, 2 ions, and then you have your salt bridge, and on the reduction side we actually have permanganate and manganese and H+ being present here, and the electrode this time is inert. We call this an inert electrode because it just needs to be there so for the electrons to be ejected into solution, right? So electrons here are flowing from the oxidation through the light bulb, and then are conducted and ejected here, where they are taken up by, of course, the manganese, as we did earlier in an earlier lecture. This is manganese +7, and so there are 5 electrons that are being taken up by the permanganate, and so we don't write the water because, you know, water is a liquid, and it's not part of it's part of the reaction, but water is the solvent. So that's just the cell notation. You should be aware of it. You should be able to construct this kind of picture based on this notation. And let's take a look at the kind of current that we can produce. So we looked at this chart earlier. There are listed as reduction potentials. All of those reactions on that list, and you know, I printed mine out, and I have all of those. That's an important list that you also might want to print out. I have it listed on Blackboard. You can download it as a JPEG, or you can probably just retrieve it from the internet as well. But obviously, we can't measure the reduction potential of a single reduction reaction. We have to. You wouldn't have a flow. You have to compare it to something, right? Like the copper and the iron, we compare it, and then we can determine the potential between those 2 electrodes, the reduction and the oxidation. So what we have is we have a standard cell, a standard, and that's the hydrogen electrode, and we make that 0 volts. Okay, so the reduction of hydrogen ions to hydrogen gas has an electron potential of 0. Of course, that's completely arbitrary. It's made up, and then you can measure it with respect to the copper or the zinc, and then you can actually get an electron potential. And we call that the standard hydrogen electrode here, the She. All right. And that is also noteworthy that this is at 25 degrees Celsius, and it's a 1 molar concentration. So temperature will affect the electron potential, and so will concentration. We will look at that later on. Let me just look at a snip of that table that I was just holding and waving in front of you. So here again we have the standard hydrogen electrode here with the 0 volts. But if I look at any of the others, let's take a look at this one. Now this is not the copper going to copper 2. It is actually copper 2 going to copper 1. So there's 1 electron reduction, and so it's listed as the reduction here. And I'm just going to relist what is already there, and we would have a 0.16 volt electron potential if we paired it up with the hydrogen electrode. And so this actually would occur in it would go from the more negative to the positive. So we would actually, this would be the anode and this would be the cathode. Okay, and so the reverse would happen here. You would have to flip the this electrode here. You would have to go hydrogen would go to hydrogen ions, and to electrons this would be the anode. And but I actually wanted to show you, and then this is unfortunately still 0 volts, but if the reverse was to happen, if I flip the copper reaction, then, and I'm kind of running out of space, but if I reverse this, copper plus goes to copper plus 2 and 1 electron, then I would just simply give this a negative 0.166 volts, right? So half reactions with a stronger tendency towards the oxidation than the She have a negative value for the standard potential. Not in this case. It would be anything that is lower, right? So here we have these negative numbers. But if we write any of them in the reverse reaction, we just simply change the sign. And anyway, so I might give you a redox reaction and ask you what the electron potential is of that cell, and also if this is a spontaneous reaction or a non-spontaneous reaction. Now, let's look at the oxidation reduction between zinc and hydrogen ions. And so it's written already in the proper form. And so if you look at the chart, step 1 should be you look at the chart of those electron potentials. And so you would find the one that's written above, written in the reverse, obviously because they're all written as reductions. And since this is a smaller number than 0, it would be listed below. So you'd find the, and again, it's going to be listed like that, zinc and 2 electrons going to zinc solid, and then it would have that negative 0.76. And so what you would do is you'd single those two things out, then you get these two numbers, and you determine that it flows from the lower to the higher, or from the more negative to the more positive. So that makes that the anode, and if it's the anode, it's the oxidation. So you have to write this reaction in reverse to make it the oxidation, which is what we have done here in this step. We've written it. And the cathode stays the way it is because that is the reduction. The reduction takes place at the cathode, the positively charged. And so you can calculate the electron potential simply off this scenario, simply, and so yes, you can also answer that this is a spontaneous reaction, right? So it will spontaneous flow from the more negative to the more positive. If it was the reverse, you'd end up with plus 0.76. Hang on. So we're going to do the electron potential of the cell is going to be equal. This will all make more sense in a minute. The electron potential of the cathode minus the standard, the half cell of the anode. Right, so we have cathode, which is 0 minus 0.76, which gives me a positive number plus 0.76. And if it's positive, it's going to be flowing in that direction. So this is spontaneous. If it was the other way around, if I wrote this as the reduction and this as the oxidation, we would of course have 0.76 minus or minus 0.76 minus 0, which would give us a negative number. So that is a non-spontaneous reaction. But so when we come back, we're going to practice a few of those, how to calculate the electron potential, and getting closer to the end. Looking forward to it.